Welcome to Digital Signal Processing Lab. So in this particular video, we are going to uh, conduct one experiment, and the objective of this experiment is to generate a discrete cosine signal. So to start with, first of all, we will be look at if we want to generate a discrete cosine signal, then this discrete cosine signal could be a periodic signal or it could be a non-periodic signal. So first of all, we have to see what will be the condition for a periodicity. So let's see if we are having any discrete exponential signals. So let us suppose that if we are having a discrete exponential signal, which is defined by this particular expression to the power j omega n, and if this particular signal is to be periodic with the number of samples equals to capital N, then this particular mathematical relationship has to be followed. Okay, so it should be e to the power j omega naught in bracket k small n plus capital N, where this capital N denotes you the number of samples. It is the periodicity in the number of samples in the form of in terms of number of samples, and that will be equals to e to the power j omega n if the signal is going to be periodic. So to be periodic, this particular condition should be followed. So that leads to this e to the power j omega n e to the power j omega naught into capital N should be equals to n should be equals to 1. So if you follow this particular condition, then it is mathematically equivalent to this particular condition. Okay, so this omega naught multiplied with the capital N should be equals to 2 pi multiplied with the small m. So where small m is an integer number, it can be 1, 2, 3, 4, anything. Okay, it can be any integer values, right? So it means that if we want to calculate this, means if we want this particular discrete exponential signal to be periodic, then we have to remember that this ratio omega naught upon 2 pi should be a rational number. If this omega naught by 2 pi is a rational number, then we can easily calculate it. We can easily say that it is a periodic number. It will be a periodic signal, right? If it is not a rational number, in that case, it will not be a periodic signal, right? So this is the condition for the periodicity that we have to remember. So here we can see that if it is a rational number, in that case, we can easily calculate what will be the period in terms of number of samples. So here you can see that this capital N will be equals to 2 pi divided by omega naught multiplied with the M. So this way, we have to first of all verify that whether the given discrete exponential signal is a periodic or a non-periodic signal, right? So if we are talking about the discrete cosine signal or discrete sine signal, the whatever be the condition for your discrete exponential signal, the same conditions will be also be followed by your discrete cosine signal and sine signal, that we have to remember. So let's see one example. Okay, so how to conduct this experiment. So let us say we are having this particular signal, right? Xn equals to cos 2 pi n upon 12. So let us say that we have to generate this particular signal 2 pi n upon 12. So first we have to verify whether this particular signal is a means a periodic signal or a non-periodic signal. So as I said that here you can see that this particular omega naught value is equals to 2 pi divided by 12, right? So this is 2 pi divided by 12. So what was the condition for the periodicity, and what will be the periodicity value? Capital N. So this capital N, we have already seen this capital N is equals to this number, right? Capital N is equals to 2 pi divided by omega naught. So there we have this omega naught equals to 2 pi divided by 12. So this number will be coming out as N equals to 2 pi divided by 2 pi divided by 12, right? So 2 pi will be cancelled out, and you will be getting N equals to 12 multiplied with the small m. So this small m at this particular case, it will be equals to 1, and we will be getting this periodicity in terms of number of samples and equals to 12. So here we can see this particular signal. If we plot this particular signal 2 pi n divided by 12, here 12, this number itself reflects the its periodicity, okay, in terms of number of samples. So here we can see that how to generate the same signal using the MATLAB. So we have to write few codes. So here we can see that the first line is CLC to clear the command window screen. This clear instruction we have to write for removing all the previous variables that we have generated. And here I'm just taking this time period in terms of number of samples, okay, while running this particular code. So this will be saved in the variable capital N, okay. So this time period and number of samples will be stored in this particular variable in capital N, right? And then here you can see that I have defined the time index variable, which is going from 0 to 5 into capital N, right? So it will be generating total 5 cycles. So as per your requirement, you can control the number of cycles that you would like to generate. So here you can see that because it is a discrete cosine signal that we are going to generate, this small n, which is the time index, it should be a integer value. It cannot be a fractional numbers, right? So it is varying from 0 to 5 into n. So n will be an integer number. So again, it is going to, if it is 12, then it will be going from 12 multiplied with the 5. So it will be 60. So it is going from 0 to 60, right? So that way you can select your time index variable. So here I have just written the same signal that is given in the book. So it is OpenM's book. Okay, so you will be seeing this particular expression that I have implemented, cos 2 pi n divided by 12. The same equation I have written, 2 pi n divided by capital N. So if you execute this particular code, okay, so once you will be executing this particular code, then while running this code, you will be asking you to give this time period in number of samples. So here, yes, we have to give this value equals to 12, right? So once you will be giving this as 12, you will be able to get this particular signal. So here you can see that we can verify that it is a periodic signal, because here you can see this this is our first sample, right? And this value is coming as 1. And here you can see again after 11th sample, okay, sir. After 11th sample, the 12th number sample is having the same magnitude. So here you can count these samples, right? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and again 12. So it is the 12th number sample which is having the same magnitude. Okay, so therefore it is going to be a periodic signal, right? So here we are getting a discrete cosine signal which is having periodicity equals to 12. So that you can verify for any of the samples. Okay, any pair of the samples you can consider. So if you see this sample, then this magnitude is coming out as 0.866. So here you can again see this particular sample is having the same magnitude, 0.866. So this way you can verify its periodicity. So we can also test with the other signal. Okay, so if you see this second signal, xn equals to cos 8 pi n divided by 31. So obviously, if you wish, you can calculate what will be the periodicity. So that n will be equals to, we have to first write 2 pi divided by omega naught. So here this omega naught is 8 pi divided by 31. So you write 2 pi divided by 8 pi divided by 31. So you will be getting 31 divided by 4, right? So this number which is coming out as is 31 divided by 4. Then here we have to choose a small m equals to 4, so that this multiplication, this product will become an integer number. So obviously it is going to be this periodicity is going to be n equals to 31, right? So 31 will be the periodicity. So after 31 sample, this periodicity is going to be repeated. Means the same sample is going to be repeated, right? So we can also implement this onto MATLAB. So here we can see, if you write the same thing, it is, we have to just write this number as to be 8 pi. Okay, so if you write 8 pi, and if we execute this code, you remember we have to write this capital N equals to 31 now. So if you write 31, and if we see this output, okay, so now here you can see this output. Okay, so total 5 number of cycles we have plotted, right? And here you can see this periodicity, right? So if you see this particular periodicity here, you see this first sample, right? What is the magnitude here? You can see. So it is, this magnitude is y equals to 1, and it is the 0th number sample, right? So because we are saying that it's means periodicity should be 31. Okay, so here you can see this another sample which is having the same magnitude. So here you just see its magnitude was 1, and you can see this magnitude is not equals to 1. It is 0.979. Okay, again, it is obviously these magnitudes are lesser than 1. This is again, if you see this magnitude, it is 0.979. But here you can see this particular sample, right? So this particular sample is having its magnitude equals to 1, and it is the 31st sample if you count it from this 0th sample. So obviously it is its periodicity is 31, right? Again, you can see because it is 31, another sample here, which is having its magnitude equals to 1. Okay, so you can see this magnitude and the sample number, it is 62, right? So this way you can see it is a periodic cosine signal, and its periodicity is equals to 31. Okay, so this way you can verify its periodicity. If you are having any doubt regarding the periodicity, if you see, maybe you may be thinking like that, if you consider this particular sample, then this sample is having sample number is x equals to 8, and its magnitude is 9795. But again, if you see, it is the sample number 23 and the magnitude is same. Okay, so after 8th sample, if you see how many samples we have got to reach to 23, it is 23 minus 8. So if you see, it will be around, yes, it is 16. Okay, so if you have, sorry, it is 15, right? So 15th number sample, okay, is having the same magnitudes. Here you can see again, right? So if you add on, right, you will be getting the same samples, right, of the same magnitude. But the problem is that it is not valid for all other samples, right? Some samples looks to be like having a different periodicity, but you cannot say that it is periodic, because if you see this periodicity, here and here it is periodic, right? These two samples are having the same period, okay, of 31 samples, right? From here to here, if you go, it will be 31 sample, right? Because if you see for the other samples, this periodicity is not equals to 15 or 16, right? And therefore the actual periodicity is 31. So that you can verify from this graph itself. Okay, so now we can see another example. Okay, just for the sake of completeness, if you see, we have another example. This is cos n equals to cos n by 6. So here you can see that we are having n by 6. So as I said that if we calculate this omega naught upon 2 pi, that should be a rational number, right? So because here we don't have 2 pi, right? So if you calculate omega naught here, it is equals to 1 by 6. Okay, so if you write 1 by 6 divided by 2 pi, then you will be finding that this value is coming out to be 1 upon 12 pi. Okay, so this is not a rational number. Okay, so therefore this signal cos n by 6 is not a periodic. It is not having a means it is not a periodic signal, right? It will be a non-periodic cosine signal. So therefore, if you plot this, you cannot identify what will be the period of this particular signal. So that you can also plot here. Okay, so let me plot this signal. Okay, if we take cos n by 6, cos n by 6. So just let me remove this one. Okay, so if you keep this as n by 6, so just we have to execute it. If you substitute 6, we are going to get this particular waveform. Here you can see this is the waveform, but you have to be very sure that this particular waveform is a non-periodic waveform. It is a non-periodic cosine signal. Remember, okay, it is a non-periodic signal. It is not having any periodicity. That you have to be sure. So I hope you must be able to understand how to generate a discrete cosine signals. Okay, so you can again, you can just look at this particular code. It is a very simple code to generate a discrete cosine signal. So try this one, and you can also verify this particular graph. Okay, so you just see this particular graph. Okay, so this particular all cosine signals you can generate. Here you can see this is cos 0 into n, cos pi n by 8, and this is cos pi n by 4, cos pi n by 2, and so on. Okay, so you please try to verify this all signals, right? You can verify this all signals, okay, by just writing these codes. So hopefully you must have understood how to generate a discrete cosine signal. So be connected with the channel for more updates. So thank you for watching this video.